Hello everyone, welcome back to 3 Deviations. In the last video, we covered how we could use linear approximations in differentials to get a better intuition of the derivative and find some applications. We're going to search some more applications of some of the methods we've learned with exponential growth and decay. Now these won't be your run-of-the-mill pre-calculus exponential growth and decay problems because we're going to be throwing a little bit of calculus in here and giving a little bit of a preview into something called differential equations, which we will revisit later on in the course in Calculus 2. So let's get started. And of course, I recommend a background knowledge in pre-calculus and in calculus. So let's begin. So the foundation of exponential growth and decay is given a function with exponential growth f of x, and this usually is some natural exponential function with e to the x, and that says that our derivative, or the rate of growth or decay, will be some constant k times f of x. And this is because when we take the derivative of e to the x, it gives us a constant out front. And again, just to belabor what we're doing a little bit, we're going to be trying to find that rate of change of exponential growth. Now let's cover some of the pure math that we're going to be doing, and this is called the law of natural growth and decay. So this says if I have a derivative of our function y with respect to t, that's going to be ky, so it is proportional to our function y, or derivative will be proportional. And y prime of t can be rewritten as an arbitrary constant c times k e to the kt, which can be rewritten as k times our arbitrary constant c e to the kt, which can be rewritten as ky of t. So we are proportional to our function y of t. Okay, so now let's talk about initial value. So y of 0, y naught, sometimes they write it as y naught. I'll be writing it both ways. It's more of a physics-like way to write it. But our initial value, y of 0, y naught, is equal to c e to the k times 0. And of course, if I multiply anything times 0, I will get 0. And then if I raise anything to the 0th power, I will get 1. So that will just leave us with c. Now notice, y of 0 is equal to our arbitrary constant c. Okay, so this is going to be helpful. So y of t, our function y of t, is going to be equal to y of 0, our initial value, c, e to the kt. And that is our function that we are going to be using a lot. We're going to be using this function a lot, and we are going to be using this function a lot. All right, let's do some examples. So we're actually going to be taking some examples from some Calculus BC exams. This one is from 1985, question number 33. And this question asks, if dy dt equals negative 2y and y equals 1 when t equals 0, what is t for which y equals 1/2? Okay, so what we're going to do here is we are going to just state what the values we know are. So k equals negative 2 because dy dt equals ky. So we're multiplying a constant by y, and that constant is negative 2. That means negative 2 equals k. And that's going to imply that y equals our initial value, y naught, e to the negative 2t, because our function y of t is equal to y of 0, e to the kt, and negative 2 is k. And we know that y naught is 1, because when our value t is 0, y is 1. Okay, now let's use this information to determine the value of t. So if y equals e to the negative 2t, notice how y naught is 1, so that y naught is going to go away because it's just 1, so we don't need to write it because multiplying anything by 1 is just itself. And that will give 1/2 e to the negative 2t because we are setting y equal to 1/2. And then if we solve for t, that is going to give us t equals negative 1/2 natural log of 2. Okay, and that was our first example. Let's do a second. We're going to take an example from population growth. So that's where this example is applied. They're telling us to use the fact that the population was 2,650 million in 1950 and 3,040 million in 1960 to determine the growth rate and the population in 1993. Okay, first what we are going to do is we're going to make this a little bit easier for ourselves. We are going to make an initial value in 1950. So we are going to set t equal to 0 in 1950, which will imply that p of 0 is equal to 2650 million and p of 10 is equal to 3040 million. Okay, and all of this is going to be in millions, so we don't need to write tons of zeros afterwards. So we are going to set our function p of t is equal to our initial value, 2560, e to the kt. We don't know k yet, but we're going to try to find that out. We are going to use p of 10 equals 2560 e to the 10k because we know t is equal to 10 because that is what we are setting our variable to. And that equals 3040 as we saw up here in 10 years after 1950. And that will imply that k is going to equal 1/10 the natural logarithm of 3040 over 2560, which is around 0.017185. And I recommend that you use a calculator on these problems just because you're going to want a nice constant in your k variable. Okay, now we can use this to make our function, our most complete form of our function. P of t is equal to 2560 e to the 0.017185t. Now that we know our function, we can find our population in 1993. So, in 1993, p of 43, 1993 is 43 years after 1950, p of 43 is equal to 2560 e to the 0.017185 times 43, our t variable. And that is roughly 5360 million. All right, that is our second example. And this is basically what our exponential curve looks like. If we plot p with p and t, we're going to get a curve that looks something like that. And of course, this is scaled. These are in increments of 20, and then p is in increments of around 1,000. Okay. So now let's talk about compound interest. So in pre-calculus, we talked about how compound interest can be discussed in increments of different time periods. So say $1,000 is invested at 6% interest annually. After 1 year, it is worth 1,000 times 1.06, which is $1,060, meaning the general equation is 1,000 times 1.06 to the t. So find the value of the investment in 3 years. So again, in pre-calculus, we talked about how we can use these different time increments to get more continuous. But with calculus, we can get continuous interest. We can compound continuously. So let's try that. So we're going to take our function a of t equals a, not our initial value, times 1 plus r over n to the nt. But we're going to attach a limit as n approaches infinity so that we get continuous compounding. And that will give a of t equals a naught our initial value e to the rt. This is very similar to the equations we saw earlier. And if we differentiate this, we will get our initial value a e to the rt. And of course, this shows that our rate of change is proportional to our function because we just have a constant being multiplied by our original function a of t over here. Okay, so now let's use this to solve our problem. So we are going to need to find a of 3. And what we are going to do in this case, we're just going to say $1,000 times e to 0.06 times 3, our time variable, and that is going to be equal to $1,197.20. And that is our third example, I'm pretty sure. All right, let's do one more example. And this is going to be from another AP BC Calculus exam from 1988. This is question number 43. We often see bacteria questions in these exams, so it's good that we're covering this. Bacteria in a certain culture increases at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, in how many hours will the number of bacteria triple? Okay, so we know it's proportional, so dy dt is going to be equal to kt. So now that implies that 2y naught equals y naught e to the 3k, because in 3 hours, it doubles. 2 times our initial value is equal to our initial value e to the 3 times k. Now we can use this to find k, divide by y naught, and take some properties and take a natural logarithm. That will give the natural logarithm of 2 over 3 equals k. Okay, so now we can further use this information to continue solving our problem. Now we want to find when the bacteria triples. So 3 times our initial value is equal to y naught e to the natural log of 2 over 3t. And that is our k value, and we're multiplying that by t. We want to solve for t. We are going to divide by y naught and do some more manipulation to give us 3 equals 2 to the 1/3 e to the t, and that will give the natural logarithm of 3 over 2 to the 1/3. And furthermore, that will give us the answer t equals 3 times the natural logarithm of 3 over the natural logarithm of 2. And that is in how many hours the number of bacteria will triple. Okay, I hope this was helpful. We sprinkled a little bit of differential calculus into some exponential growth and decay problems. Again, we will be seeing a lot more of this in Calculus 2 when we will be even more involved with these differential equations that we were working with today. In the next video, we are going to be talking about some of the applications of this elementary differential calculus that we've been talking about to the natural sciences, chemistry, biology, and physics. Furthermore, we will be moving on to our third unit to cover how we can use derivatives to even further connect our intuition of graphs. All right, thank you for watching.